Hello. So in the introductory video on Joule-Thomson effect, we have discussed the main features of that phenomenon, whereby I told you that depending on the nature of the gas, either it may get heated up or it may get cooled down, or in some particular cases like that of ideal gases, there won't be any effect at all. Means you cannot have any sort of cooling effect in the case of ideal gases. And now, in order to distinguish between the various types of Joule-Thomson effects, we will be developing its necessary theory starting from the basic thermodynamical equations, and we will start by defining what is known as the Joule-Thomson coefficient. Hope you remember, while we discussed about the Joule effect, we had introduced a coefficient known as the Joule's coefficient, which was represented as something like dot T by dou P at constant internal energy U. This quantity was named as the Joule coefficient. You can just refer back. Now, the same manner, in Joule-Thomson effect, we will be defining a new quantity which is nothing but measured as dot T by dou P itself, means rate of change of temperature with pressure. But the difference is that it should be measured at constant value of enthalpy. Hope you remember in the introductory video we mentioned that throttling process or the Joule-Thomson expansion is an isenthalpic process, whereas the Joule expansion was a process happening at constant internal energy. So that is the difference in the definition of the two coefficients. So dot T by dou P at constant internal energy is known as Joule coefficient, a quantity that is related to the Joule expansion, whereas dot T by dou P, the rate of change of temperature with the pressure at constant enthalpy, is known as the Joule-Thomson coefficient, or it's also known as Joule-Kelvin coefficient. And we will see that how this particular mathematical parameter or quantity is helpful in analyzing the nature of cooling or heating during the throttling or the porous plug expansion. So we have the basic definition of the Joule-Thomson coefficient here. The rate of change of temperature, that is dot T, right, with respect to pressure, that is dou P, at constant enthalpy, that is by there is an H here, is known as the Joule-Thomson coefficient. Now we will derive shortly the expression for Joule-Thomson coefficient, and also we will analyze its importance. So what we can do, we can just start off from our basic concept of enthalpy as a function. We have seen enthalpy was one amongst the 4 thermodynamic potential functions that we have discussed. So we have seen that H, the enthalpy, is expressed in terms of its natural variables, namely the pressure and the entropy. So we can see H can be expressed as H of PS, right, from which we wrote, we have, so we can just start with, we have H is equal to H of PS. Oh, then I can say therefore I can directly write what is the differential of H for any infinitesimal process. What will be dH equal to? dH equal to, hope you remember this equation, we had 4 Gibbs equations or 4 Gibbsian equations, out of which dH was equal to TdS plus VdP or VdP plus TdS, whatever it is. remember that whenever TDS and VDP terms are there, both of them are positive. That was one of our memory aid or mnemonic that we have discussed earlier. So let me start from this equation. I think that will be easier. So DH is equal to TDS plus VDP. And now see, what will be the value of DH for Joule-Thomson expansion? That should be equal to 0. Why? Because this effect is isenthalpic since H equal to constant. So this is a particular case. So H being constant, DH is equal to 0, right, for this particular process. So we start from here. Let me say that this is my equation number 1. Let me call this equation number 1. Fine. Now you know that the entropy can be expressed as a function of any of the remaining 3 variables, right? Also, so I can just say also S, the entropy of the system. I can write S as a function of the pressure and temperature of the system. You can understand why we begin with this particular form of the entropy, because we are interested in the Joule-Thomson coefficient, which is nothing but relating dot T with the dot P. So pressure and temperature should be with our should be with us. That's why I'm just using. Whereas hope you remember that while we discussed about the 3 TDS equations, I told you from the entropy functional dependence we have a possibility for deriving 3 TDS equation. So we derived first TDS equation, and the second TDS equation I left you with just discussing or finding out the third TDS equation and all, where we used 2 of the functional dependence, PT and VT dependence was used. So once again we begin with this particular expression, S is equal to S of PT. Okay, so it is up to us to decide which functional form of the particular quantity is to be used. It depends on our motivation, what we have to finally arrive at at the end of our discussion, right? So S is equal to S of PT. Now from that, can you just write down what will be the differential change in S for an infinitesimal process? Therefore I can write therefore ds is equal to, ds is equal to, what will be ds equal to? Can you just use the chain rule in partial derivative? That is what? Dou S, we are familiar with that one. Dou S with respect to dou P at constant is not temperature times what? Dou S by dou P at constant temperature times dP, right? Plus dou S with respect to dou T, keeping the other variable, which is the other variable, that is pressure constant, times what? dt. Let me say that this is my second equation to begin with. Now what we are going to do is that just this second equation can be substituted in the first equation, where you can see in the first equation there is ds, and I'm going to substitute for this ds in terms of equation number 2. Okay, so equation number 1 becomes, is it not, or substituting, you can understand from the next step, substituting 2 in 1, what do you get? You get anyway that is equal to 0. So I can write t into, so ds is a lengthy expression, so let me write it like this, t into let me write, yes, dou S by dou P, dou S by dou P at t. I have to reproduce the same thing at t times dP plus dou S with respect to dou T times P dt. Okay, so that is substituting for ds plus VDP, right? Plus VDP, that is here, from here, plus VDP, that's equal to 0, right? So that is my relationship. Now let's do some rearrangements. What rearrangement can be done? Can you look at this expression and see that there are 2 terms with the dP? Okay, 2 terms with the dP. So you can just combine their coefficient and write as a simplified equation. So what I will write is this one, and see, or I can do one more step, and I can take the dt term to the other side, right? Okay, so I'm separating out two things. Therefore, this one you can just skip. So what I'm writing is this one. So there will be t multiplied with, right? So I'm writing t into dou s by dou t. Just look at the expression, you will understand. I'm opening this bracket and then, okay, t into dou s by dou t at p times dt. So I'm keeping that term on the LHS, and I'm taking the other two terms combined to the other side. So what will be the thing? So there will be a negative sign, right? You can just expect a negative sign. So minus, so let me just use a square bracket once again, minus t into dou s by dou p at t. So this is what I'm just taking, these two, right? And dp is just, you know, it's common, so I can put plus v, right? So from this v, so plus v, right, times dp. Is it not right? So I have just put a negative sign here, so that justifies my see, rearranging to the RHS. So that is the thing, right? Now let me give some name for this one. So let me name it as some equation number 3. It's up to us, right? Now just one more thing, let's again simplify this equation number 3. So can't you see that here there is on the LHS t dou s. What is t into dou s by dou t? Can't you rearrange this one? See, hope you remember that. But okay, if you want, you can write. See here, I'm writing it here. But t into dou s by dou t at p can be written as, what is t dou s? We have already seen that it can be written as dou q or dou bar q, whatever it is. Okay, so it will be dou q by dou t, okay, from the definition of ds. So you have ds is equal to dq over t. So on cross multiplying, it will give you what? T ds is equal to dq, or t into dou s will be equal to dou bar q, okay, or dou q. So at constant pressure. And what is this dou q by dou t at constant pressure? Hope you can clearly recall that this is nothing but our heat capacity at constant pressure for the particular gas in question. So it's Cp, right? So I can replace this thing with the Cp. So what will be this equation becoming now? So this equation will further become Cp. For this entire thing, I'm substituting it as Cp. So it's Cp dt. Cp dt is equal to, on the other side it's the same thing, minus, one more thing I can do, see, minus t into, you can skip some of the equations and all, okay. See, can't you see that there is a dou s by dou p, and you know, we have a dislike towards this differentials of s. Why there is a dislike? Because you have seen that the entropy is not a directly accessible or directly measurable quantity. So it's always better that we convert those equations with dou s or ds into some other equivalent equations. How do we do that? For that, we have to depend upon what is known as what? The Maxwell's relationships. And that is one of the prime importance or relevance of Maxwell relation. We can express those hard to measure quantities in terms of easily accessible or easily measurable quantities. So I think you can just find out what will be the Maxwell relation for dou s by dou p at t. So let's try to recall it. It's good that you apply it frequently. Dou s by dou p, okay, at t, what it should be, okay. Let's first write on it. Let's write out, you know, by the cross multiplication rule, I told you that the cross multiplying things should be always conjugate to pair. So it is p in the denominator, so it should be what? V, right? So it should be V. So I'm writing dou V. So here S is in the numerator here, so it should be, okay, it's conjugate. What's the conjugate of S? That should be what? Okay, right, you know, it is T. So it should be dou V by dou T. It's quite easy if you follow the mnemonics that we have discussed in our previous modules, previous sessions. Okay, now one more thing you have to do. See, you have to keep what is constant. So you know the conjugate of numerator will be kept as a constant. So V is here. So what will be the constant here? P is the constant, right? Now one more thing is left out. What is that? You have to check whether the equation will be plus or minus. Okay, what do you say? Will this relation be plus or minus? You know, only those relation with p and t on the same side as the numerator or denominator will be positive. Here, you know, p and s are on the same side, so this equation should essentially be having a negative sign. Got it? So by Maxwell's equation, you can identify that this one was discussed as the fourth Maxwell equation. So by okay, Maxwell's equation, okay, whether it is first, second, or third, or fourth, that doesn't matter. The thing is that you should be able to recall it. Okay, so by Maxwell equation you can use this one. So there is a negative sign, and I'm applying once again a negative sign here, so that the equation will become positive finally. So it will be just what will be the equation? Dou v by dou t. Am I right? Dou v by dou t. So it is minus dou v by dou t at constant pressure plus v, right? Okay, so it was plus v here, plus v times dp times dp. Now you can just make some modification. Okay, once again, so I'm doing it here. So that is cp dt, which is further equal to, I got to return it here, so I can get rid of the negative sign. Yeah, of course I have to take the negative sign inside, so it will become simply what is that? T into I need not use, okay, right? So t into, yeah, okay, I have used the negative signs. T into dou v by dou t at constant pressure, so that term has become positive, but the v term will become negative. Okay, so that is minus v times dp, right? Yes, so that is the final expression that is with us now. Okay, you look at what is our we should not forget what was our actually aim. What's the aim that we are trying to do? We are trying to obtain an expression for the so-called Joule-Thomson coefficient. And what is Joule-Thomson coefficient? That should be always with your z derivation. That is the ratio of dou t dou p at constant h, and we have been doing the process for constant h, so it doesn't matter. So I need to get dou t by dou p. So can you get it from here? So here on the left side you have got dt, and on the right side you have got dp. So can you get dt by dp? Or okay, finally, so therefore I can say, on rearranging this one, on rearranging this equation, therefore I can say dou t, right? Instead of dt I am writing dou t upon dou p, rearranging, bringing this p from that here. So why I say? Because we have mentioned that the h is remaining constant. That's equal to, that will be equal to what? So you take this cp to the other side, so it will become 1 by cp times the remaining thing, whatever it is. What is that? T into dou v. It's a bit lengthy, but see that dou v upon dou t at p minus v. Okay, so and this quantity is usually represented by the letter mu, Greek letter mu. Okay, and we call this one as some equation number 4. So it's up to you to decide the number of equations and all, and see, this is exactly what we finally need, and we were in search of this particular expression. See, this is the expression for what the so-called, what is known as what, the Joule-Thomson coefficient. See that, you okay, memorize it and give the due importance for that. Hope you understood how to derive the expression for Joule-Thomson coefficient. It's quite easy. We will begin with the isenthalpic nature of the throttling process, and we used the entropy dependence, functional dependence of entropy in terms of pressure and temperature. We wrote ds and we substituted, and in between we just used the Maxwell's fourth equation, and then we were able to obtain the expression for dou t by dou p at constant h. Okay, so that is the expression here. Okay, so we can just modify this equation in terms of what is known as volume expansivity, and I think I will do it in the next video. Okay, so by the time just go through this one and try to understand the derivation. Okay, thank you.